What's up, everyone? We're moving into section 5.3. We're going to study the ellipse, which is our third conic section. So let's just start with the geometric definition for the ellipse. It's known to be the collection of all points in the plane, the sum of whose distances from two fixed points, called the foci, is a constant. Now, foci is just the plural of the word focus. So this definition is showing us that an ellipse has two focus points. If you were to pick any random point on the ellipse and measure the distance from that point to your two focus points, and then add those two distances up, you will always get the same value. All right. So let's give you an illustration for that. All right. So here is the ellipse in blue. It looks like an oval, and you have this random point P in pink on the ellipse. You also have your two focus points, F sub 1 and F sub 2. Notice they are both inside the ellipse. If I measure the distance right now from this point P to F sub 1, I have a distance of 11 units. And from point P to F sub 2, the distance is 5 units. And then, of course, the sum of those two distances is 16. All right. Now let me move around P, and we'll see which numerical values change here. You can see that as I'm changing the location of P, of course, the distances from that point to your two focus points, they will change. But see how the sum is always remaining 16 units. Okay. All right. Now let's talk about the different characteristics of the graph of an ellipse. All right. So an ellipse has a major axis, which is the line containing the foci. All right, it's the line containing the foci. So right here, the horizontal line that passes through F sub 1 and F sub 2, that would be considered your major axis. The midpoint of the line segment joining the foci is called your center. So the center is literally halfway between the two focus points. And then the line through the center that's perpendicular to your major axis is called the minor axis. Okay, so right now the minor axis is a vertical line. And then you have the concept of vertices and co-vertices. So vertices would be the 2 points of intersection of the ellipse and the major axis. So the blue points, these are my vertices. And then my co-vertices are the 2 points of intersection of the ellipse and the minor axis. So my green points here are my co-vertices. Okay. Also notice in the picture we have a couple other things labeled. So you have the semi-major axis. That's simply the line segment that's stretching from the center of the ellipse to either of the main vertices. Then you have the semi-minor axis, which is the line segment stretching from the center to the co-vertices. Right. You also have linear eccentricity, which is defined to be the distance from the center to either of your focus points. Okay. Now, one interesting property associated with the ellipse is that the sum that you get from the distances from each focus point to the point on the ellipse, that sum is always going to be equal to the length of the major axis. Okay, so let's illustrate that. All right, so of course you have the ellipse, you have this random point P again on the ellipse, and we're showing the distances from point P to the two focus points. And what we want to illustrate here is that those two distances are going to equal, when you add them up, the length of the major axis, which again is just the distance from vertex to vertex. Okay, and of course it doesn't matter where I place this point P, the distances from it to each of the focus points changes, but the sum will always remain that same length of the major axis. Okay. All right, now want to do a little bit of an investigation relating the equation of an ellipse to its graph, okay? And I have 4 questions on your screen that have been posed that we're going to try to answer using this Desmos activity, okay? So let's just open it up. The questions are typed into the activity as well. Okay, so you can see I have a red ellipse here, and that's based on the equation in box 2 of x squared over m squared plus y squared over n squared equals 1. And I have sliders that I can use to adjust the values of m and n. So first things we should be identifying about the equation here. Notice in order for this to be an ellipse, there's a couple really important things. Both x and y have to be squared in your equation, and you have to have addition in between those two, okay? And then we often like to write these so that the equation is equal to 1, okay? All right, so you can play around with the sliders here a little bit, and you can kind of see how they will affect the ellipse itself. So let's just tackle each one of these questions, okay? So first question, is it ever possible for the graph of an ellipse to become a circle? If so, under what conditions will this happen? So I ask this because an ellipse being an oval, it's a lot like a circle, right? And even the equation for the ellipse, it follows a pretty similar format to a circle in that both x and y are being squared and you have addition in between them, okay? So what's the difference between the equation being a circle versus an ellipse, right? So right now I have an ellipse, still have an ellipse, now it's a circle, okay? And what makes it a circle is that the values of m and n are the same now, which means your two denominators in the equation will be the same, okay? So if denominators are equal, you get a circle. If they are different, you get an ellipse, okay? Second question, how can the length of an ellipse semi-major and semi-minor axes be determined just by looking at its equation? All right, so right now, as I have it graphed, the ellipse has a major axis that's horizontal. It's the x-axis. And remember, the length of the semi-major axis would be the distance from the center to either one of the vertices. So right now, that length for the semi-major axis is 4 units, which just so happens to be the value of m, okay? Now, understand if m is 4, in your equation, you're not actually going to see a 4 because that value of m is being squared. So really, the denominator of that first fraction is 16. So what that tells me is if I were to take the square root of that denominator, it would give me the length of that semi-major axis, okay? Notice the semi-minor axis, it has a length of 2 units, distance from the center to either one of my co-vertices, okay? And the reason it's 2 units right now is because n has a value of 2. If n is 2, then the second fraction has a denominator that is actually 4. So again, if I were to take the square root of that second denominator, I would have the length of that semi-minor axis. All right, now questions 3 and 4, they kind of go together. What must happen to ensure that the graph's major axis is horizontal or vertical? And what must happen to ensure the graph's minor axis is horizontal or vertical? So right now, again, as it stands, the major axis is the horizontal x-axis. The minor axis is the vertical y-axis, all right? So you can play around with either slider to get that to change. All right, so right there is where it changes, okay? Now I have the major axis as the y-axis and the minor as the x-axis. And the reason it changed is because now the value of m is larger than the value of m. And think about how that relates to your equation. If m is smaller than n, then that means the smaller denominator is underneath x squared, the larger denominator is underneath y squared. So your major axis is simply dependent upon which variable has the larger denominator associated with it. Okay. Again, if your y squared has a larger denominator under it than x squared, then that tells me you're going to have a major axis of the y-axis, being that it's vertical. Okay. All right, so hopefully that's good insight into how the equation for the ellipse relates to the graph. All right. In our next video, we're actually going to start graphing these ourselves by hand.